So I'm going to talk about the answer, and then if we need to see it the other way, we can do that. So the method that is shown here is when you're taking the perfect squares or perfect cubes, but if you did the factoring method, that is fine too. But your answer should have been 7 times the square root of 3. Anyone have questions about that one or need to see it the other way? And then 12, your final answer should have been 64 times the square root of 2. Anyone need to see this done the factor tree method? Okay. Regina, give me the numbers you used. 3, 2, 2, and 4. So then, what did you use after that? For 16, you use what? 8 and 2. 4 and 2. And this should also be written down. Okay, so we have one set of 2s, another set of 2s, and another set of 2s. So that would be 3 sets of 2s outside times the 8 that was already there. So this would be 8 times 2 times 2 times 2. And then the only thing left by itself is 1 and 2. So if we multiply all that together, we should get 64. Other questions on that one? For number 20, you should have gotten 4 times the cube root of 3. Anyone need to see that done in the factor tree method? Or have questions about that one? Which one? You said 24? Okay. Give me 1 second on that. Do you have questions about 20 or no? Okay. Regina. Yep. What numbers did you choose? 96 and 2. And then for 96, 48 and 2, that works. Numbers for 48? 4 and 2. I'm only asking for yours specifically because everyone could have done this differently. And then for 24? 12 and 2. And then for 12? 6 and 2. And then 3 and 2. Remember, for cube roots, you're looking for groups of 3, not pairs. So groups of 3, we have these 3, and then 1, 3 by itself. So that would be 2 times 2 times the cube root of 3 left over, which would give us that 4. Other questions on that one? Remember to double check your answers at the end. If you get something and the decimals don't match the original, something's off. You're missing something. Then for 24, the final answer was negative 9 times the cube root of 7. Anyone need to see that one factor tree method? Let's go through these quick check problems. I meant to say this earlier, so if you didn't figure this out, there was a front and a back. If you didn't get to some of them because I didn't say this, that's okay. Alright, so I said do number 1 on 3A and then 1 through 3 on the other side. So the question is asking, is this in simplest form? Simplest radical form. Is it in simplest form? Can we simplify it more? Yes, we can simplify it more. No, it's not in simplest form. And the reason why it's not is because we can simplify it more. So someone tell me how they did that. Or how they would do that if you didn't get that one. Otis, go ahead.
50 is broken up into 25 and 6. 150 is broken up into 25 and 6.
Okay.
And then 25 is broken up into 5 and 5, and 6 is broken up into 3 and 2.
Okay. So then from there, what would we do? Otis, go ahead.
I multiplied my 5s together. I move my 5s out and I multiply it by -1.
Okay.
And then I have my 3 and my 2, which are still in my radical symbol, and then I multiply those together, so I get -5 radical 6.
So this would be our simplified or simplest radical form. But the answer to the question is no, because we can simplify it more. Questions on that one? Or anyone do that differently? They want to check their work? On the back, we need to simplify all 3 of these expressions. 3 is a little bit different. Anyone want to walk me through how they did number 1? Otis, go for it.
So I split up my -128 into -16 and then I split my -16 into -4 and 4. And then from -4 and 4, my -4 split up into -2 and 2. And then my +4 split up into just 2 and 2. And then I split off my 8 into 4 and 2, and then my 4 into 2 and 2. And then I move my 2 groups of 2, because we have it to the 3rd power, or it's cubed. So I move my 2 3s out. You get what I'm saying?
Yes.
Okay.
Your 2 groups of 2, you move that out.
Yes. And then I multiply those 2 together, and I get 4. And then inside the radical, I'm left with -2.
So you are really close here. We don't want that negative to stay on the inside when we have cube roots. We want to take that out immediately. So you could have immediately moved that out and said this is -1 times 128. That way we get this instead of what you have. So always make sure you take that negative out, because if you leave it in, it'll be marked wrong. Even though technically they're the same answer, you just don't see negatives still inside the square, cube root, whatever it is. Okay. Anyone want to walk me through how they did number 2? Did anyone use the perfect cube method for this? Sophia, what was the highest perfect cube that you could put into this?
27.
27 and
16.
so the cube root of 27 we know is 3. Just to make sure that we did choose the highest perfect cube, I'm going to break this down like I would normally. So we got 8 and 2, 4 and 2, 2 and 2, and groups of 3 we have 1. Because we can break this down and we got something that could come out, 27 wasn't our highest, but we can still do it this way. You're like doing kind of both methods this way. So if you got something like this and you double check, can I break 16 down anymore? Would I get a group of 3? And you do, you would bring that out and still leave whatever's left inside. What this means is if I divided 432 by the 6 cubed, which is 216, that would have worked. Because then the cube root of 216 is 6, and I'm left with the cube root of 2. So it can be done both ways, but if you are not choosing the highest cube, perfect square, you have to make sure that this can't be broken down anymore. We can't take anything else out of it. So either make sure you have the highest, or if you don't choose the highest, you're going to end up doing the factor tree and the perfect cube, perfect square method. So just keep that in mind. For number 3, student A was asked to simplify the expression. They got this. Did we say that this was correct or incorrect? Keela? You were going to say the answer. Was this answer correct or incorrect? Keila, what were you going to say? Let's see. If we could break this down, we could try perfect cubes. I'm going to just do it that method for the 1944. Let's see. 729. I don't even remember what all of them are. Whatever 8 cubed is. Yeah. 7 cubed. And then 216. 216 works. I know 216 and the cube root of 9 would work. The cube root of 216 is 6. 9 can only be broken down to 3 and 3, and I need a group of 3, so I cannot simplify that anymore. And if I check this with the cube root of 1944, I should get the same decimal. So 72 was incorrect. We could have also just went to the cube root of 72 and see if we can break that down, because if we can break that down, then this also wouldn't be the answer. Did we have any other remaining questions about this before we get into what we're going to do today? So in those same notes that we were working in last class, now we're going to talk about how to simplify with variables. The same way we simplified just numbers is going to be the same thing we do for variables. Either use the factor tree method, and I'll show you how that works here in a second, or use like the perfect square, perfect cube method, but it's a little different, so I'm going to walk you through that here in a second. So I'm going to show you the factor tree method first, and then we'll go back and talk about this rule and how we could use that rule. So x squared, and I know we haven't done exponents yet, that'll be the next unit, but if I had x squared, that's me saying x times x. And then we're still looking for either groups or pairs. Pairs or groups. So square root, we're looking for a group of 2. So this would just equal x. we're going to do another one without the numbers in front before I go back and show you the rule. So then n to the 5th, how would I write that out? Notice. 5 times, correct. So then again, we're looking for pairs. How many pairs would we have here? 2. With one left over, that one that is by itself would be unfortunate and would stay inside. But now we have to multiply these variables together. There are 2 of them, so that would be n squared times the square root of n. The issue that we come across with variables is that we can't check it like we can check the numbers because there are no numbers. So in these two of these. When you get to these, you can check the number part, but there's no way to really check, did I simplify my variables right? So you just have to be mindful of that. So if you like this method, that's fine, but be mindful because you'll get something like a to the 19. You're going to write out 19 a's. You can, or you can do it this way. So if m is a multiple of 2, use the rule, the square root of a to the m would just equal a. What this is really saying is if your exponent is even, we can divide it. So imagine there's a 2 out here. What I do is say, okay, if this is 2, 2 goes into 2 how many times? Once, so this would be a to the 1 with nothing left over. And we'll do that here in a second. If this was 4, 2 goes into 4 twice, and this would be a square with nothing left over. So on and so forth. If it's not a multiple of 2, it gets a little bit more complex. So instead of doing this, I'm still going to use that same mindset of dividing, but there would be leftovers. Like if this was 7, 2 goes into 7 how many times? How many times does 2 go into 7? 3. So that means I have some a to the 3rd, but the one that's left over would stay inside. So you'll see how that works here in just 1 second. So if we're using that method, I would put a little 2 out here and say 2 divided by 2 is 1. So this would just be x to the 1, which is what this is. All of your variables, numbers really have an exponent of 1, you just don't see it. And we'll talk more about that when we actually get into exponents, but that's okay. For number 3, if I put a little 2 out here, 2 goes into 5 twice with 1 left over. So that would look something like this. We know it goes in twice for certain. There'd be 1 left over, and that 1 would just go inside. So the work for this method, there really isn't any. You're kind of just dividing the number, seeing what's left. So in number 2, when we have numbers and variables, you have to do the method to both. So I would say think one piece at a time. First, is 9 a perfect square? Yes. What is 9? The square root of 9? 3. So this would be me doing the perfect square method because 1 is already a perfect square. And then if I wanted to use this method, 2 goes into 10 how many times? 5. So I would have k to the 5th with nothing left over. So 3k to the 5th would be my final answer. There's nothing left inside the radical. Now, I'm going to go back and do this to factor tree method. That way you have both and you see them. So if I were breaking this down, I know 9 is 3 and 3. K to the 10th, I'd have to write out 10 k's. and find all of my pairs, which would be my group of 3 and 5 groups of pairs. So everything would get to come out, nothing would be left inside. Both methods work. Do we have any questions so far? Let's do 5. That's the perfect solution. We do 4, and then we'll come back to another one. Is 40 a perfect square? No, so we need to either break it down using factor tree method or perfect square. Let's say I'm using perfect square for both. Think about your perfect squares. Try to start doing this without your calculator. Think about your perfect squares. What is the highest perfect square we can divide 40 by? 36. And get a whole number. Sophia? 16. Would we get a whole number if we divided by 16? 4. 4 would, yeah, 4 would be the highest. Sometimes the highest isn't that high at all. So we know the square root of 4 is 2. Just to make sure we didn't choose a number that wasn't the highest, if I break down 10, I have 5 and 2. Neither of those is a pair, so we're good there. So what I'm going to do is just write times the square root of 10, and then do my A's, and then rearrange and simplify. So I'm going to use this method again, where I say 2 goes into 19 how many times? 8. I think you're close. 9. There we go. So what that rule up there was really saying is that this would give me an even number and there would be 1 left over. So this would be 9 with 1 left over. So I have a to the 9th. And then the square root of a. These are a's. This one's a 9. I'm going to make that a different color. Okay, we're not. So then everything outside would be next to each other, and everything inside would be next to each other. So you'd have to rearrange. The 2 and the a to the 9th would come out front. The 10 and the a would both be underneath the rest. So 2a to the 9th times 10 times the square root of 10a. And then again, we could check the numbers, but we couldn't check the variables to make sure we did this right. What questions do we have about this so far? Oh, the factor tree method? Yeah, sure. You said 5, or did you mean 4? 5, okay. Okay, so if we were doing 5 the factor tree method way, 25 is a perfect square, but if we're not thinking that, that's okay. So we know that'd be 5 and 5. We could list out all of our x's and y's and find pairs. So x to the 6 would be 6 x's. And then 13 y's. And we'd be looking for pairs. We have a pair of 5s. How many pairs of x's? So we have 3. So no x's left over. How many pairs of y's would we have? 4. Say that again.
Oh wait, not 4.
Not 4. More than 4.
6.
6 with 1 left over. 2, 3, 4, 5, 6. So everything that is a pair gets to come out. Now if you're writing out each of these by pairs, it would look something like 5 times your 3 groups of x's times your 6 groups of y's and your 1 y that's left over. And then you would simplify. 5 x to the third y to the 6 times the square root of y. Regina.
So you have to like put I and then 3 like right on together, right?
If you just wrote x to the third instead of this part, that would be okay. I was just doing it like step by step.
Thank you.
I want to do 12. I wish these were both combined. 144 is a perfect square, but we'll still do it, whatever. Between 6 through 11, do we have any others we want to see or go over before we do 12? Otis? 9. And then which method for each thing would you like? Factor 2 method for everything? Okay. So someone give me 2 factors of 320. Kendall? 48 and 8. I think that works. No, just 40. 40 and 8. Got it. That does work. Okay. And then 2 factors of 40.
4 to 10.
Then we have 2 and 2, and 5 and 2, 4 and 2, and 2 and 2. So let's see, we have a group of 2s, another group of 2s, and another group of 2s. And then 5 is unfortunate, it stays by itself. So you have 8 times 2 times 2 times 2 times the square root of 5 as of right now. Then we only have 1 x. So that's going to be by itself regardless because it already doesn't have a pair. And then we have 4 y's. How many groups of y, or pairs of y's do we have? 2. So those would both come out. So if we start to simplify, 8 times 2 times 2 times 2 is
64?
I believe so. Yeah, because this would be 8. 8 times 8 is 64. The 2 y's would come out and be y squared. And then on the inside we have the square root of 5x. Questions about that one? Any others we want to see before we do number 12? Sheila? 8. And then with 8, would you want to see that factor tree or perfect square method? Okay. Use for the variable and the numbers? Okay. Alright. For 27, is 27 a perfect square? Yes. The square root of 27 is 3. I'm sorry. You're thinking perfect cube. It would be a perfect cube. It's not a perfect square. The closest, yes. But if we divided it, we would get a whole number. So we're thinking of the highest perfect square we can divide it by, which was that part was right. I just was thinking too much too long. The square root of 9 is perfect, and that would give us 3. So we were close, we just weren't there yet. And then 2 goes into 3 how many times? 1 time. So if I were to like rewrite this, I would say just once with 1 left over. So this would be 1 of the ends would come out, and then this 1 by itself would be inside the square root of times this. I forgot to bring it down. So on the outside, we have 3 times 1 end. On the inside, we also have 3 times n. Other questions on that one? Any others? 5, 6, 10, 11 before we do 12. It does take time to get used to doing this, but once you get it, it's not that bad. So I'm going to do 12 using your perfect square method for both, and then if we need to see it the other way, we can do that. Is 144 a perfect square? Yes. The square root of 144 is what? 12. I'm bringing down that -5, so remember to multiply it. 2 goes into 16 how many times? 8. So what I'm going to do is just go ahead and write that down. That would be x to the 8th. There would be nothing left. 2 goes into 10 how many times? 5. So that, again, would not have anything left over, so I'm just going to write y to the 5th. And then 2 goes into 7 how many times? 3. So we have z to the 3, and we have 1 z left over. -5 times 12 would give us -60. All of my variables that are outside would go in alphabetical order. And then what's left on the inside is just z. So this, the only thing you can check here is your numbers. Regina. So we did the perfect square method, not the factor tree method. Emma. Yes, I can. Give me 2 factors of 144. Okay. Do you want factor tree method for the variables too? Do you want us to write out all the x's, y's, and z's? Yes. So we have 16 x's. We have 10 y's. And 7 z's. And then we go through and find all of our picks. Say that again. Oh yeah, I am definitely going to use X's. Thank you. Okay, so pair of 12s. pairs of x's, 5 pairs of y's, 3 pairs of z's. Only thing left over is 1 z. So writing that how I see it, I have -5 on the outside times my 1 group of 12 times my 8 group of x's, or you can immediately put 8x to the 8. 1, 2, 3, 4, 5, 6, 7, 8. My 5 group of y's. My 3 groups of z's. And my leftovers. -60, x to the 8th, y to the 5th, z to the 3rd, square root of z. Yes?
Why don't we simplify the 12 more?
Oh, yep, we're definitely supposed to do that. I was thinking perfect squares more. Yep, we definitely should have done that. Yeah. 4 and 3, 4 and 3, 4 and 3. So we have a group of 2s and a group of 3s. Still get the same answer. My brain is on doing it the simplest way, so my brain got confused as well. Alright, other questions we want to see go over 6, 7, 10, 11. Jasmine. Using which method? The perfect square on, I was going to say on both, but there's only one. Okay. 2 goes into 15 how many times? 7. So if I have 7 times 2 would give me 14. So there would be 1 left over. 2 goes into 9 how many times? 4. 2 times 4 would give me 8. And there would be 1 left over. So I have p to the 4th. I didn't need it, but yeah, I did. With 1 left over. And then if this one's by itself, it has a 1. Does 2 go into 1? No. So that one would automatically be on the inside. So everything on the outside, we have p to the 7. These are definitely supposed to be q's, not p's, but disregard. My brain is like Monday brain. I don't know what's going on. It's fine. Okay, so p to the 7th, q to the 4th. Those would both be on the outside. And then everything on the inside would be P, Q, R. So this is one you could not check in your calculator and would have to go back and double check your work. So double checking, you could use the other method. So if you use this method, go back and do the factor tree. Or if you use the factor tree, go back and do this method, either or. Okay. Go to the next page. Hopefully you are getting the hang of the variables. Same thing here, except now we're going to do this with 3s. So the rule here is the same. If this is divisible by 3, you're going to have this A. But if it's not a multiple of 3, you have to think about 3 goes into it, how many times, how much would be left over. That could be 1, that could be 2, it depends. So for this one, using this rule, 3 goes into 3 how many times? Once. So that means there would only be 1 left over. If we were using the factor tree method, x to the 3rd would be x times x times x. That is a group of 3, so it would come out. Let's do 16. I'm going to do the perfect cube method first, and then if we want to go back and see the factor tree, we can. Think about your perfect cubes, write them off to the side if you need them again, or on top, whatever. What is the highest perfect cube we can divide 40 by? Sophia. 8. No, 8 and 5 would make 40. The cube root of 8 is what? What times what times what will give us 8? 2. And then if I'm using the rule method for this, 3 goes into 16. How many times? Evenly. 5. That would be 15 over 3. With how many left over? 1. So the 5 would come out. And there'd be 1 left over. I keep forgetting stuff. This is supposed to get brought down too. So we have the negative 3 up front, times 2 times the cube root of 5 times w to the 5th times the cube root of w. So I'm going to rearrange all of that before I simplify it. And then simplify it. So negative 6 times w to the 5th. If you want to use parentheses, now would be a good time to do that, times the cube root of 5w. Do we want to see that factor tree method? Yes. So do you know the number and the variable? Yes. Someone give me 2 factors of 40. Jaden.
2.
Sure. So then for 20, give me 2 factors. 10 and 2. And then for 10, we have 5 and 2. Remember, we're looking for groups of 3. We do have a group of 2s that would come out. So far we have negative 3 times 2 with our cube root of 5. Then for 16, we have 16 w's. And we're looking for groups of 3. So we have 1, 2, 3, 4, 5, with 1 left over. So if you're writing them all out, 1, 2, 3, 4, 5, with 1 left over. And then simplifying this, we have negative 6 times the cube root of 5 times w to the 5th times the cube root of 5 of w. No. And then rearrange it again. So you get the same thing either way, just one takes a little bit longer. Questions about that one? Either method? Find another one you see you want to do. You said the perfect cube. Okay. And then Kendall, you had your hand raised? Okay, cool. So if we're doing this the perfect cube way, is 250, well first, let's take this negative out. That way we don't have to worry about it later. Is 250 a perfect cube already? No. Okay. What is the highest perfect cube we can divide 250 by? Think about your perfect cubes. $125. 125 and 2 would give us 250. I'm going to do the numbers and then go back and do the variables. So the cube root of 125 is what? 5. So this would be -1 times 2 times 5 times the cube root of 2. So we got our numbers part down for the most part. And then for our variables, 3 goes into 3 how many times? Once. So there would just be 1 A. You can put H to 1, you can just put A, it does not matter. If you want to like show that work, because it only goes in once, that would be the same as 3 over 3. So we got 1. 3 goes into 4 how many times? Once also. But we would have an additional leftover. So we have A times the cube root of A. And then we can simplify and rearrange. So on the outside, -1 times 2 times 5 times A times A. So -10 A squared would all be on the outside. On the inside, we have 2 and A. So it would be times the cube root of 2A. What happens to what? I did forget about the B. Alright, let's go back and do that. Yeah, it was supposed to be B, not A. That's fine. Okay. That's the same thing I did with the P's earlier. Brain just not working. Okay, so this is going to change a little bit, because this would just be A. This would be B with B. There we go. I'm making mistakes all over the place here. I'm sorry. Questions on that one? Sophia. How is it to say that question again?
How is it 2 A instead of just 2 B cube?
Oh yeah, the A wasn't there. That was my bad because I was looking at other things. So just 2B underneath the cube root. I don't know why I put that there. It shouldn't have been there. Definitely should not have been there. Kendall. Yes. Okay. Pick another one. Mm-hmm. What was that? 2 times the cube root of -250. Okay. Still take your negative out. That would still be step 1. Give me 2 factors of 250.
125.
Give me 2 factors of 125. 5 and 5 for 25. Then you're looking for groups of 3 so that 5 will come out. I'm like running out of space, so we're just going to write this where I have space. So negative 1 times 2 times 5 with that cube root of 2. And then we have a to the 3rd, b to the 4th. So we would have our group of a's that would come out. We would have a group of b's that would come out with 1 leftover b. And then we would put everything together. Negative 1 times 2 times 5 times a times b. Negative 10 a b. On the inside we have 2 and b. Pick another one you see that you want to go over. Which method? Okay, so we'll do this. For the number, factor tree or perfect cube? Okay. For the variables, perfect cube or factor tree? Okay. So for 192, think about your perfect cubes. What is the highest perfect cube we can divide 192 by and get a whole number? That's right. 27 wouldn't give us a whole number. I heard 64. Yeah. So the cube root of 64 and the cube root of, what was that, 3? Yes. Cube root of 64 is what? That's the square root, the cube root. 4. Okay. 3 goes into 8 how many times? 3 times. Twice. So 2 times 3 would give us 6. And there would be how many left over? If it only goes in twice. 2. So we have 6 divided by 3 is 2. So 2 on the outside and 2 on the inside. For our S's, does 3 go into 2? Evenly? To get a whole number, I should say, because 3 is not even. No. So that would automatically go inside the cube root. 3 goes into 18 how many times? 6 times. With nothing left over. So that would just be t to the 6. So putting everything we have together on the outside, we have 4 r squared t to the 6. On the inside, we have 3 r squared s squared. Other questions about that? Okay. I'm going to give you a couple problems to try. If you finish these before class ends, bring them to me. 5. Number 11. 5 and 11. Are those two? Let me know.